Making predictions. We're going to use both our exponential and logistic model to make some predictions. But first of all, here's a very simple graph. If we start off with I0 infections, K is our carrying capacity. With an exponential growth function, this just takes off exponentially, goes sailing past K upward to infinity and beyond. With a logistic model, we never surpass the carrying capacity or the maximum infected population. So although initially they may look the same, and commonly people say viruses grow exponentially. Well, for a short duration in the beginning, exponential and logistic growth look a lot alike, and how long they look alike, a lot of it depends on how big I0 is relative to K. If I0 is really small relative to K, they can look a lot alike for a pretty long period of time. If I0 is big relative to K, they diverge very, very early on. So let's look at our first example. Suppose we already have this model, 20e to the 0.13, I forgot the 9 here, 139t. We've already established that. We had an initial population infected of 20, and in 5 days it doubled, we had 40. How many infections will we have in 180 days, roughly 6 months? We're basically saying T is 180 days, and we can calculate I equals 20e to the 0.139 times 180. And we're just going to calculate that. This E, on many calculators, is just second natural log. So there's so many different calculators out there. There's even online scientific calculators that have interesting user interfaces where you just have to plug it into a template. So I'm not going to get into the details of how to figure this out in a particular calculator, but we can do and we get a ginormous number, 1.469 times 10 to the 12th. Okay, that's trillion infections. You can see what happens. There's only billions of people in the world, roughly 7 billion. So this just increased beyond belief. And obviously that's not true. The virus growth is not exponential over a very long duration. So this logistic model corrects for that, of course. When will we reach 1,000 infections? Well, we're really saying I equals 1,000. So we can substitute 1,000 right in here and solve for T. And so we get 1,000 equals 20e to the 0.139 times T. And we're solving for T. We can divide by 20. 1,000 over 20 is 50, equals e to the 0.139 T. And then we'll take the natural log of both sides. Let me erase a little bit of this. And so we will have, let's come up here, 50 equals e to the 0.139 t. And we're going to take the natural log of both sides. Natural log 50 equals natural log e to the 0.139 t. Of course, a natural log and the exponential function basically are inverses. And so we have ln 50 equals 0.139 t. Divide by 0.139. And we get t equals ln 50, 0.139. And we can calculate that. And it looks to me like we get roughly 28 days, or about a month. It takes about a month for 1,000 infections. So, okay, let's look at this model. We can even do the same questions. We're going to change this model to 200 divided by 1 plus 9 e to the negative 0.162 t, and ask ourselves how many infections in 180 days, and also when will we reach 1,000 infections. Well, let's start with our 180 days. We're going to substitute that here, and we have I. You can put I of 180 here if you want, or you can just say I equals, that's up to you. 200 divided by 1 plus 9 e to the negative 0.162 times 180. And of course we can calculate that. And we end up getting 200. In reality, it's probably 199.99999. But my calculator rounded up to 200. We've reached as close to full infection as we can. So we probably would have reached that much earlier, actually. But we're right up near carrying capacity. When will we reach 1,000 infections? That's very easy to answer, never. Because 1,000 is past here. You can try to solve this using logarithms. You can plug 1,000 in here, solve it. You'll end up trying to take the logarithm of a negative number, which doesn't exist. Some calculators will give you an imaginary answer, but there's no real-time t at which this will happen. So let's change this up a little bit. Let's change this to 199, just for this question only. If we're really close to 200, we have no idea how long we were close to 200. So this will tell us when we reached a 99.5% infection rate for the population. Well, we can plug in 199 here, and that's equal to 200 divided by 1 plus 9 e to the negative 0.162 t. And then we can cross multiply, and we get 199 times 1 plus 9 e to the negative 0.162 t equals 200. And we can divide this, or we can multiply it. It doesn't really matter here. I'll multiply it out. We got 199 plus 9 times 199 equals 1791 times this exponential decay factor. Then we're going to subtract 199. And we get 1791 equals 1. Divide by 1791. Okay, now 1 divided by, if we're working with 3 significant figures, you can approximate that to 3 sig figs if you want. Make it a little simpler, we get 0.000558. Let's see, it's 0.00558. And that would take the natural log of both sides. Natural log cancels out this. Negative 0.162t is equal to natural log 0.000558. And t is equal to natural log 0.000558 divided by negative 0.162 equals it looks to me like we got 120.8 or about 121 days. So we've reached that. We reached 199. Really, 2/3 of this 180 days. We were up close to 200 pretty quick. Okay. Hey, kitty cat. Here, sunshine. Say hello to the class. This is my rescue kitty. She wants to be on camera. Hey, kitty cat. Okay. That's all for this video.